So we have this second talk in the afternoon session by Professor Greg Michael. You're actually British, right?
Sorry?
You're actually British.
I'm British, yes.
Yeah, because you should not pronounce your name in the German way.
Michael.
But he's working at the Free University in Berlin. We call it Freie, of course. Okay, great.
So mixing of the lunar regolith by impact. What remains at the surface from the basin-forming event? So what remains on the surface today? So in this talk, I'm going to essentially talk about two different parts. The first is the results of aggregation of radioisotope dating analyses of impact melt from the Apollo and Lunar samples, and also from lunar meteorites, which are another source of samples from the moon. And then the larger part of the talk will be about modeling of the transport of components of the lunar regolith, or possibly we'll call this mega regolith, carrying different potassium-argon age signatures by impact processes. So I make this distinction between regolith and mega regolith because when people refer to the regolith, they're normally understanding this as the very fine material, just in the upper few meters of the moon. But actually the regolith can also be understood as all fragmental material, which has kind of been thrown onto the surface by impact ejecta. And that can be seen at fine scales, which is this dusty material on the surface, but it can also be seen at much larger scales with very large pieces ejected by impact basins. So this has sometimes been referred to as the mega regolith to distinguish the two. And at the end, I'll wrap up the talk by going back to look at the results of isotope dating in the context of what the model seems to show, and seeing if it can help us to understand what it means. So here you see on the top right, you see an example of an Apollo 17 fragmental breccia. And you see that this rock, it contains lots of small pieces of what we see them as different colors here, but they are pieces of different composition from different origin. So the impact processes on the moon, they cause this massive fragmentation and remixing of material continuously throughout the moon's history. And so when you pick up a piece of rock from the surface of the moon, you're actually holding pieces of rock which originated in many, many different places. And there's a lot of information in every piece that you pick up. Some of these components can be identified as being impact melt. And impact melt can be dated with the potassium-argon radioisotope method. And this allows us to measure the time since that particular component was last heated. And when we say heated, we're talking about something like greater than 500 degrees C as a heating event. Potassium-argon dating relies on the decay of potassium-40 to argon-40, which has a half-life of about 1.3 billion years. And if the mineral is cold, that argon-40 remains trapped in the lattice structure of the mineral. If it's heated, then the argon can escape, and that's how the resetting mechanism works. In the highlands of the moon, the only significant heating process is by impact. So when we see resetting of the potassium-argon clock, the typical cause on the moon is by impact. Over here on the left, you see the results of aggregating about 270 published potassium-argon datings of highland rock samples. These are from Apollo 14, 15, 16, 17, and Lunar 20. So I was working with Sasha Basilevsky, and he went through all of the published data that he could find on this, and we put them all together into these aggregated views that you see on the left. So in these 6 plots, you've got Apollo 14, 15, 16, 17, Lunar 20 on the bottom left, and on the bottom right, you've got a combination of all 5 of those, so those all aggregated together. And what you see in these plots, the different colors actually represent different categorizations of the components that were dated. The most important ones from our point of view are the impact melts, which are represented by the cyan color. But we also have, you see, breccias with no melt, which are dated in green, and we have rocks with igneous structures. So these are some kind of possible melts, but possibly not identifiable from their structure as impact melts. So it's a rock that was formed by heat processes. And then in gray, on every one, you've just got all of the data totally together. And what was recognized very, very early on after the Apollo missions, you see in this Terra et al. Paper in 1974, was that you see at every site of Apollo, you see this very strong peak, which is close to 3.9 billion years, 14, 15, especially in 17 and 16. Interestingly, in Lunar 20, this peak is not so strongly developed. There's some older material there, and we'll come back to that later. When everything is totaled together, well, this peak is very strong indeed. It's marked here at 3.87, and this led to the idea that something special happened on the moon at 3.9 billion years, and the idea at the time was that there was a lunar cataclysm. So something happened on the moon that meant that there was a very large amount of impacting going on. Okay, the other source of data that we have, or the other source of samples that we have from the moon are the lunar meteorites. And you see in the picture here on the right, this is a similar picture. This is a lunar meteorite fragmental breccia. You see it's got a very similar kind of mixed structure to the one we saw before. We have 23 lunar meteorites, and 94 clasts have been dated from these 23 meteorites. 2 of those are pairs of meteorites, so they probably come from the same location. So possibly these represent 21 different locations on the moon where the meteorites were ejected. When we plot all the data together in the same style, you see that there's this kind of continuous distribution of ages between about 4.3 at the oldest, going down to about 1.3. There possibly is a stronger signature around the 3.9, but it's not in any way dominant as it was in the samples from Apollo. So this cataclysmic peak is much less pronounced if you look at the data through the meteorites. Okay, putting them side by side, well, there's the possible interpretation that because all of the Apollo landings were in a rather small cluster around the center of the near side, the lunar landings actually, interestingly, were further off to the east. It could be that the reason that we see this very strong signature around 3.9 is that this is a characteristic of this area. And we're seeing the same thing because we're sampling the same thing. The possibility is that because the lunar meteorites are randomly sampled from the entire lunar surface, this is more like the picture for the whole of the moon, and what we're seeing from Apollo is a signature of the region around the Imbrium Basin. The Imbrium Basin is this one here, and of course the ejector from Imbrium would be very strongly located around that area. So could it be that the difference is between the two is that we've got a sampling bias and that actually there was no special event at 3.9. This is what we tend to look at with this model. So what abundances of differently aged components should we expect to see at different places on the moon? We've got a lot of the information that we need to find the answers to this. Since the time of Apollo, the chronology system for the moon has been developed a long way. We have crater chronology systems that describe the complete history of observable bombardment. It describes the changing impact rate on the moon, and it describes the size frequency distribution of craters that form on the moon. This is one side of the story. The other side is that we have a growing understanding of processes and conditions of impacts at different scales, and also the resulting temperature distribution that occurs within the target after impact. So we can have some idea of how the potassium-argon age signatures should change within the material, both within the crater and within its ejecta. And we also have some idea about how material is redistributed during an impact. Single impacts have been studied very well, and we don't know about large basin impacts, but these have been simulated with finite element models and different kinds of models, so that we have at least some understanding of how ejection works at all scales. And if you put these two things together, this allows us to build a model that traces the evolution of the abundance of components with different age signatures across the surface of the moon. So in building the model, what do we look at? Impacts, of course, they occur at random locations on the moon, although it has to be said that in reproducing a model, we can't simulate basins as forming at random locations, because the basins that formed on the moon formed in the locations that they did. We could simulate a different moon where basins occur randomly, but if we're interested in biases which are likely to come from the particular basins, we need to simulate the basins as they actually formed on the moon. Each impact produces a quantity of heated material with a new age signature. This material is distributed inside the crater, and it's also distributed within the ejected unheated material. So we know that the majority of material that is ejected from an impact is not heated, it's ejected cold. There's only a small fraction of it which is close to the impact boundary, which gets to temperatures which are high enough to reset the potassium-argon clock. At any given location, a sequence of layers of ejecta builds up, and each layer has its own composition of different ages. If you want to build a complete model, there are potentially 4 different dimensions to this. There are the X, Y, and Z positions, but there is also the composition at any point. So I'm not quite sure when it cut, but I was just saying that there are potentially 4 dimensions to model, X, Y, and Z in composition. In this simplified first variant, we exclude the X and Y and model only the depth and the composition. So the next few slides show how the model works. So the initial state of the model, we say we start off with the moon, which is in a nominal starting state. So we label the whole material of the moon with a starting age. So say 4.5 billion years. We begin the clock. We select a minimum crater size for simulation, so that can be something like 5 kilometers, but it can be any other value depending how detailed you want it. This value determines how many impacts are going to occur over the whole period of the model. So this block here represents the material of the moon, and we're looking at the dimension of depth below the surface. These 2 plots that you see here, they're probably familiar. The one on the left shows the impact rate function from Neukomm's 1983 chronology model. It shows that in the early times of the moon, the impact rate was much faster, and then it decays down to 3 billion years. It reaches a constant state and remains constant from thereafter. On the right-hand side, you see the function that represents the size frequency distribution of crater formation on the moon. So this kind of wavy curve You've got, it's a cumulative function. So you have diameter on the bottom axis here and the cumulative crater frequency. So that's the number of craters forming larger than the given diameter against diameter. So it has this form. So we've chosen a particular minimum size of crater to simulate, and we can use this rate function to look up the impact rate at a given time. We have to rescale it to the size of crater that we are working with. That's this d min, and we can do that by looking at the 1 kilometer size on here and the d min size on here, and looking at the ratio between the two values to rescale this rate function. And then we use a Monte Carlo approach to calculate the time to the next impact event. And we use a Poisson function to find realistically distributed time intervals when we know that the average time interval is lambda t. So the Monte Carlo method generates the crater diameter for each impact, and then we use, well, the way that the Monte Carlo method works is that you generate a random number with a uniform distribution, and you want to map that uniform random number onto an actual crater diameter. So if you look at this plot over here on the right, you can generate the uniform random number represented by u here between these two extreme values, and you look up the crater diameter that corresponds to that random number. And by doing it this way, you generate a random population which conforms to the size frequency distribution that you see in this wavy curve. Of course, what we see on the moon are the final states of formation of impact craters. So after, especially for the large ones, you have a transient cavity which collapses to a final state. When we're thinking about ejection of material, it's actually the transient cavity diameter which is important for calculating volumes, etc. But we can use this equation from McKinnon et al. 97 to transform the observed crater diameter back to a transient cavity diameter in order to go on with the melt calculations and ejection calculations. Here's the next step where we look at excavation and heating and melting. So this is a diagram from Mellish, which roughly explains what happens to the different parts of the crater, or different parts of the target material after the crater is formed. So you see that the ejected material is initially in this area here. It's a kind of torus around a central area. This part in the center is vaporized. This part in black is melted. The lower part is displaced. And what we're interested in particular is how much of this material is ejected. So the depth of excavation is calculated from Mellish. So that's about 1/10 of the transient crater diameter. And the ejected material has this torus shape and is about 1/3 of the volume above this 1/10 of diameter depth. A small fraction of that excavated volume is considered to have been heated or melted above the point required to reset the potassium-argon clock. That's described by this equation here. And in the simulation, this material which has been heated is marked with the current clock time in the simulation. So this introduces into the model the resetting event by the heating. This schematic diagram shows, essentially how the model works. So an impact occurs, the excavated material is redistributed evenly over the entire surface of the body. So you see it like this. Most of that material is cold, so its age signature is unchanged. but a small component is heated and develops a new age signature. So in this diagram here, the red spots represent the material that has been melted and has got a new age signature. But the gray spots, they are just fragmented material from below, but they still carry the same potassium-argon time signature as they had before the impact. The intent is to obtain an average picture of the lunar state of composition versus depth. And okay, it may seem strange to make a one-dimensional model like this, but actually it's not so far from being reasonable, because the relative high frequency of smaller impacts whose ejector does not travel so far balances the neglecting of the impact location. So eventually we obtain an average picture of the quantity of ejector sourced from craters of different sizes at any point. Here you see a second impact occurring, which penetrates the first layer on the surface. It creates a new set of melt, which is colored with the blue color, and you see deposits a new layer on the surface containing mostly material which has been unheated. So you see there are a lot of gray spots in there. You see there are a few red spots in there which were excavated from the top layer and replaced on the surface. And there are also blue spots which represent the new impact, the impact that occurred then, which has a new time signature. So inside the model, you know, how do we keep track of this? This is basically what it looks like inside the model. So you start off with time 0. You've got this thick layer here. It has an arbitrary thickness of 100. And all of it is purely of time 0. So these numbers here represent the fraction of material in the layer which has that time signature. So all of it has time 0. After the first impact occurs, we now have 2 layers. We have the bottom layer, which has got a little bit thinner, but it still has this pure time signature of T0. And then we have the top layer, which is represented by this line here. This is a very thin layer on the surface. Most of its time signature is still the original time signature. It's 97% of the original T0 time, but a small fraction of it was melted and got a new time signature T1. Then you see this progresses, the same thing happens again. We've got another impact occurs. You see the bottom layer remains pure T0, the second layer remains as it was. The third layer has become more complex again. You see most of the impact penetrated into the deeper layer here. So most of the material is still from T0. A small fraction was melted, about 3% was melted and became T2, that's the new one. But a very small amount of this thin layer here was also excavated and redeposited onto the surface. And that's what you see with this 0.001 here. So you can imagine that as you keep going with these with different diameters and different impacts, you build up more and more layers, and you manage to keep the story of how the melt is developing, how the melt mixture is developing. Another thing that we need to keep track of is mass conservation. So we need to trace the age composition by volume and account the material precisely. When an impact penetrates a layer, as you see here, the volume of that layer is diminished. So of course, if we're looking at the real moon, we kind of cut a hole in that layer and we redeposited the material elsewhere. Yeah, the amount of ejecta from a given impact residing at a given depth is diminished by having holes punched in it. But in a 1D model, we can't record holes. So what we do instead is reduce the thickness of the layer in the same way to account for the volume reduction. So we calculate what the hole would have been and relative to the area that we're considering, and we, instead of punching that hole, we just diminish the thickness of the layer to keep the volume of that material as it should be. And then we iterate the model. So we go on and produce the next impact and produce the next impact of the next diameter until we reach the present day. So that may be tens or hundreds of thousands of impacts. Okay, I mentioned earlier on that it's necessary not to simulate the formation of basins in a random sense, but actually to replicate what we actually see on the moon, because eventually we want to replicate the distribution of material exactly as we see it for our moon, not for a random moon. So the way we do that is to take we take 30 known impact basins. The impact basins are not included in the production function because the production function only goes up to 300 kilometers. So we simulate these basins individually. We establish a plausible distribution of time points for the basin forming events as predicted from the N20 crater densities measured by Facet et al. So we know the density of 20 kilometer craters on the ejector, for example, of these basins, and that allows us to approximately put them in an age sequence, and the 20 kilometer crater density even allows us to estimate some kind of reasonable sequence for their ages. So you see in the standard Neukom model, using the N20 densities from Facet et al., we can estimate that the basins could have an age range that looks something like this. Now, of course, individually there will be errors in that, but that is kind of how the picture should be. So the latest basin forming around 3.85 for Orientale and going back to 4.2 something for the South Pole 18. The black lines in these plots represent the 5 basins that are named here, and all of the blue lines, there are the 25 blue lines in between, they just represent the other basins that occur in between those. Now we want to look at some possible cataclysm scenarios, and how the cataclysm actually was. There have been many different suggestions for how that might be. But one possibility is it's just like a kind of a Gaussian peak that occurred at that time. We don't really know what the how the rate function might look behind the cataclysm peak, because if you have a cataclysm, that tends to hide any information that comes from before that time. But these are 2 possible scenarios for how the cataclysm might look. So this would be a small cataclysm peak, and you see the effect on the basin formation is to bring, well, with this small peak, it brings some of the smaller basins forward, not South Pole Aitken, but you see Nectaris, Crisium, Imbrium, they're all shifted forwards in time. So now they look more like they're around 3.9 billion years rather than being back at 4.1 or something like that. If you have an even larger cataclysm, then that brings everything forward. So you know, with a cataclysm peak like that, you would expect that all of the basins formed within this very short period between 3.8 and 3.9. We can put these different scenarios into the model, and then we can have a look and see what comes out, and we can compare that to the data that we actually have. So here I show the first outputs from the model. These are for a standard scenario, so with a rate function that looks like this. What you see here are 2 realizations of the same model. So remember, it's a Monte Carlo model, so it's using random numbers in the generation of the impact craters. So the models shouldn't necessarily look exactly the same every time, but it's useful to see what comes out the same and what comes out different if you run the model twice. So what we're looking at here, these plots are quite complicated. You have Here on the bottom, you've got time. Over here represents melt that was produced close to the present day. So any features you see in here are potassium-argon time signatures. And so here's the present day, here's the start of the model at 4.5. On the y-axis here, we have two different scales. So the outer scale here is the depth in kilometers on a logarithmic scale. So here we're looking at very thin layers close to the surface. Here is 1 kilometer below the surface, 100 meters, 10 meters, 1 meter, 10 centimeters, 1 centimeter. So we're even looking at the very thin stuff right at the surface of the regolith. And then you see that there are various horizontal traces within this plot. Each of these horizontal traces is a histogram, and it's a histogram of the age composition of material at the depth of the baseline of the trace, a kind of compound plot. So at the surface, we see material which has, were we to pick up a sample of this and were we able to date it perfectly with every component with the potassium argon dating, we would expect to see this. There's quite a lot of material with old age signatures which comes from the basin formation time. So you see that these large black bars, these are that's the South Point Aitken, and the other peaks you see here are I think the last one is Orientale, and that one might be Imbrium. And then you see right close to the present time, you see some more peaks. And these peaks represent the very last events that happened on the surface. So of course, there are two different things happening here. Like a very small impact near the surface produces a small amount of melt, but it leaves that melt right on the surface. And so if you pick up stuff from the surface, you can see some very recent events. But there's also material which comes from early times, which, okay, this goes down to very great depths, and it's been recycled up and up and up and up to the surface. Every time an impact occurs, it throws up some of that material again, and so it remains on the surface of the moon forever. And then there are the intermediate times where you see material here, like some larger events that occurred in the intermediate time. So here's one at like 1.7 billion years and the one at 2.5 billion years, where you can still see signatures at around 10 meters depth. So these would have a strong signature at 10-meter depth, but you can also see that some of this material has been recycled up to the surface, not in such great abundance, but you can see the trace of that right up to the surface, and there are small peaks here where that's coming onto the surface. Okay, in a second simulation of the same thing, you can see some of these characteristics are similar. So we see the same characteristic for the early time that looks almost identical between the two realizations. The recent time is a bit different because in a different Monte Carlo realization, the impacts which occurred slightly differently with different sizes, but we also see the same idea that you can see the very latest impacts close to the surface. They leave a strong signature at the surface. And there are other things in intermediate which are around 10 meters depth, 1 meter to 10 meters depth. But it looks different because that depends on what size of craters actually occur. Takeaway from this is that at the surface, the most common melt that you find is actually the melt from basins. So even at the surface, the most common thing you expect to find is melt from basin impacts, but with an admixture from the most recent stuff. Another interesting outcome is that these numbers which are down the edge, these are also a part of the histogram, but they're not plotted because they're such large numbers, but these represent the amount of material which remains at T0. So it's the material which has never been heated in the whole history of the moon. And these are quite large numbers. So the model is predicting that you can find material at the surface which has never been heated by impact, and so should be older than 4.2 billion years. Okay, here are the results for the two cataclysm scenarios. And what you see is that when you add a peak into the scenario, it causes a concentration of melt at that time. No surprise, of course, and the stronger you make the cataclysm, the stronger the signature it has at the surface. The basins ages are spread forward in time, and the peak is precisely reflected in the presence of melt from that time throughout the depth range. So not only is it at the surface, but it goes through all depths down to a kilometer or so. So this should definitely be visible in the samples. So now we come back to compare these models with what we had at the start. Okay, so if you believe in a cataclysm scenario that looked like this, the prediction of the model is that it should produce a signature that has this strong peak that looks like this, and that is exactly what you saw in the Apollo data, so that makes perfectly good sense. But if that is the case, you also expect to see that in the lunar meteorite data, because the lunar meteorite data is a sampling of the whole surface of the moon, and that signature should be present everywhere. It's not the case here, this is a weaker one. In the standard scenario, the old basin melt is spread over a wider period. It looks more like this. You know, if you look at this, this kind of distribution, it's more like what you see here. Of course, you can't make an exact reproduction one from the other, because this is only 20 samples on the left. But it is also plausible that, you know, what we're seeing here corresponds to what we're seeing here. And that would suggest that what we're seeing up here is you know, or in these peaks, this is not a picture of the whole moon, it's a picture of a local bias around the Imbrium basin. So in conclusion, the model that we built, it captures the process of mixing by impacts, at least in an average sense. It predicts the abundances of components of different ages, and by ages we mean the time to the last heating event, in correspondence to depth. And it's plausible to suggest that the standard scenario explains the highland meteorite age distribution, and that the return samples are showing a local bias from basin-forming events. That's the paper that we had in 2018. Now, we're trying to take this model further. Essentially, the ideas are exactly the same, but this assumption that we made, this simplification that we made to remove the X and Y coordinates, we're trying to go back on that and actually carry out this modeling for cells over the whole surface of the moon. As you can imagine, the number of computations that go into this, it was already quite high, and when you put it into 3 dimensions, that makes the problem very much more difficult. But we have done some of this, and the first results are quite promising. So what you're seeing down here in this plot, which comes from a paper by Tiantian Liu, this is a plot of the present day distribution of Serenitatis melt down to 10 meters depth. So this colored scale bar on the right shows the fraction which comes from Serenitatis. And so there are places where, you know, obviously this red circle is Serenitatis itself. There you expect to find very large quantities of Serenitatis. Actually, this is neglecting the mare which are formed over the top, which is another complication that is coming into some later works. But if we were looking at impact only, you would expect to find the most impact melt, of course, inside the Serenitatis basin, And then you see how it's spread over the rest of the moon. And the rest of the spread is very much controlled by the other impacts which occur after this. So you see there were some large holes where another basin has formed, and that completely obliterates the presence of Trinitatis melt. There are other places where it's just been re-ejected and thrown further. That's what we're seeing with all this grey material. And there are many places where it's got holes punched in it, where it's been re-excavated, and you can see higher concentrations, lower concentrations. It's quite a complicated picture. The idea is that this kind of modeling can guide the choice and set expectations for new sampling sites on the moon. And eventually we think that this type of modeling has to become an essential part of understanding what lunar material is. Everything on the moon is connected with this recycling from impacts, and you can't understand what you're picking up without understanding how the impact mixing process occurs on the moon. Thank you for your attention.
Yeah, great. Thank you so much. I mean, you have explained this, the simple part of your modeling, you know, the complicated part still to come, right?
Well, I think actually the conceptual part is all in here. What comes in as a complication later on is mostly to do with the computational details, like putting this into 3 dimensions is a horribly difficult problem computationally, but the ideas are the same. Okay, there are some new clever parts that Tiantian has put in where we do start to consider the formation of the mare surfaces and how that plays into the recycling process. And you suddenly get a new layer of material that covers everything up. And then you get new impacts which can either throw material onto the mare from outside, or they can puncture the mare and bring up material from underneath and throw it on top. This is also very interesting. That's
the dating you mentioned are mostly done on the lunar rocks, or could the grains, you know, you have the dust particle, could you also use them for the dating?
I think as it stands, the dating is done on relatively large particles from the lunar samples. And that's not to say that it can't be done on smaller particles, but the larger ones are obviously, so far, they've been easier. You know, that's the place to start, because you know more what it is you're dealing with. If you can pick out a melt particle which is a few millimeters, you know that you've got something homogeneous, and you can understand what it means when you get an age for that. I have been talking to the people who do some of this dating about what it would mean if you were to look at some of the much smaller grained material in the breccias. So as I mentioned back here, our model predicts that there is a lot of material which has never been heated, at least not within the history of the observable basins on the moon. So this material should predate the oldest basins that we see on the moon. But the likelihood is that the more times material gets recycled, the finer it gets crushed. So if that material is present in the samples that we've got, it's likely to be the very finest material. And unfortunately, that means that it's very mixed up. And when you take it, you're not going to be able to get any individual particle that has an individual age. You're going to have to take a collection of particles and try to make some sense out of dating an accumulation. Well, there are other complications to do with that because of for potassium argon, at least, the argon is captured in the mineral structure. If you grind it too finely, then the rates of diffusion of argon out of those particles become different. You know, the general assumption is that it's large enough that it's not diffusing out. Probably this won't work for potassium argon, but there are other dating systems where it might be possible to do some things like that.
You know, in this slide, you have two runs, number one, number two, but they also in the middle of it, you have this horizontal, you know, track. They're quite similar. What's the reason? Because you are doing a Monte Carlo, and then there must be a something behind it to have this kind of, you know, similarity.
Do you see my mouse pointer?
No.
No. Okay. So you're talking about the track that's
right. I mean that you see these two diagrams. You have about 0.48, 0.47, 0.48 on the horizontal scale, and there you have a horizontal tracks, and
yes.
that here in both runs.
Yes, yes. So those represent material that is at about 10 meters depth.
And then because they don't get destroyed easily, so they kept there.
Yes, that's right. So this process of excavating material and throwing it onto the surface, excavating and throwing it onto the surface, for material between about 1 and 3 billion years, that process only gets down to a depth of about 10 meters. Mm-hmm. So anything deeper than 10 meters should be older than what you see there.
Okay, that's the reason. Okay, I think that explains it. Yeah. Any questions from the audience to ask Greg? You know, I think this modeling is quite interesting and promising, and give us a complete new way, you know, to on understanding the dating.
This is my feeling too. It's a different way to look at the problem, and even though okay, what came out of the modeling,
it's a very nice.
It's only a new look at the ideas that were already there. The idea that okay, maybe there was a cataclysm, or maybe this is local bias. That those ideas already existed before this modeling, but with the modeling, you can actually see how it gets to those states. And by refining this model, eventually, I hope that, you know, if we've got a spatially refined model like this, we can say, okay, we should go to such and such place on the moon and take samples there. We should go to such and such place, and then we start to see some differences, and then we can.
Yeah, and at least you can say that, you know, okay, if you want to prove me wrong, you know, you run your own model, right?
That's right. That's right. Well, this is the process that occurs on the moon. There's no doubt about that. The details of this model may need a lot of refinement, but you know, this is definitely what's happening. So that's the way to understand it.
One final question is that in your very last slide, you mentioned that the lunar meteorites, you said is Highland meteorites. How could you tell they are from Highland?
I'm not the meteorite expert, but they can recognize meteorites that come from Mars surfaces because they're mineralogically very different.
But on the near side, you also have a highland, a crater region. It's not so different from the back side.
Well, when I say highland, I'm referring to any surface which is not a Mars.
Oh, okay. Not from the far side. Okay, that's true. Yes.
So to me, that's the distinction between old surface which is purely impact modified and surface which is volcanic.
Yeah, my mistake in misunderstanding that sentence. Okay, great. Anyone have questions here? And you better unmute yourself and ask quickly. If not, I can see that you have two papers, new paper. One is published in last year, right? 2020 in Icarus.
Yes.
I better look it up, you know.
Yes. So that's the first one from the three-dimensional model. 2020.
Okay, great. Thank you so much, you know. And And I hope you will be able to go to Freie as soon as possible.
Thank you. Thank you. Thank you. No, it's a very nice idea to have this kind of international seminar. Yeah, I see the audience is not very large, but it's a nice idea because you could potentially have many people joining from many places.
And later, I mean, because later they found that, you know, they can go back to the, you know, to the videos.
Yeah.
So eventually it would be it's the cumulative idea. If you have people in Freie who would like to give talks, you know, on the moon, and just let me know.
Okay. Okay.
Okay. Yeah.
I could talk to Chen Tian. She might like to do that.
Oh yeah. Okay. Good. Yeah. Yeah. Ask her for me.
All right.
Yeah. Thank you.
Okay. Thanks very much.